All right, so today we're finding the trigonometric value within any angle. So normally we think of for finding trig and right triangles, but it can apply to any angle. And actually we can use this knowledge, see if we continue it, to apply to regular sine and cosine functions. But anyway, so in this circle, we'll notice we want to find sine of theta. And theta, by the way, will always be the angle closest to the origin. So inside the blue vectors there, we have our blue angle. So that's the angle I need to find. Here's why. Because, what if I did that? Wouldn't I make a right triangle? Yes. And if I make a triangle there, I need to find out what that angle is so that I could do my trigonometry from there. Because I'm assuming it's going to be a special angle, either 30, 60, or 45, so that I can find my side lengths. Because if they don't give me the length of the vector, I won't have any idea what those angles are unless it's a special right triangle. So anyway, here we go. I like working with degrees better. And here's a little hint if you have radians going to degrees. Whenever it's pi over 6, it doesn't matter what the number in front of pi is, but if it's pi over 6, that will be 30 degrees. So, excuse me, that would be, 30 degrees. So that means, if I were to multiply this by 180 over pi, which is the ratio you'd use, 6 goes into 180 30 times. So that's why I say you multiply it by 30. So 35 times 30, so you have to do a little math here. 35 times 3 would be 70. And then add another, that's 105. So that's 1,050. 1,050 degrees. Okay. So 1,050 degrees all the way around. And notice how I'd make 1, 2 rotations, and I get stopped there in the third. So if I make 2 rotations, let me subtract 720 from that to know how far I went in the third rotation. So 1050 minus 720 is going to give me 330 degrees. Okay, so I know that, let me do a different color here. I know that from where I started all the way to here in the third rotation, I went 330 degrees. So that means to go the rest of the way would only be 30 more degrees, right? To go all the way around would be another 30 degrees, or another way to think about it, if I connect my angle to the x-axis, like I did with the dotted line there, I'm connecting it to the part where I get to 360. So 330 minus 360 equals 30 degrees. So this triangle I have is a special right triangle. And here's why that's significant. If it's a special right triangle, I already know the side lengths. Cool. So opposite of 30 degrees is 1. Opposite of the 90-degree angle or the hypotenuse is 2. And opposite of 60 degrees is radical 3. Now, of course, we always have to be aware of what quadrant we're in because that's going to make the side lengths positive or negative. But in the first quadrant, the x values are always positive and the y values are always positive, so we're good here. And then when we do our trigonometry, we always do our trigonometry from the reference angle, which was right there, okay, that will be where theta is. And I like labeling all my sides here, so the opposite from that angle is the 1, so 1 is opposite. The hypotenuse, of course, is the hypotenuse. That's going to be 2. And radical 3 is the adjacent side. All right, it said to find sine of that angle. So sine, if I remember SOHCAHTOA, sine is opposite over hypotenuse. So my opposite side is 1. My hypotenuse is 2. So that means sine of negative 35 pi over 6, or sine of negative 1050, is 1/2. Wow, so that kind of combined all of our knowledge we've learned about graphing angles outside of a triangle or a geometric shape, and then applying that to special right triangles, which you guys have learned before, and then applying that to trigonometry, which you've learned before, to find what the sine of any angle could be. So it could be ginormous, it could be huge, but we can still find it using our knowledge of special right triangles and graphing rotations. So that is the gist of how you find a trigonometric function inside of a circle or with rotations.